All right, welcome back. Some physics of music. We're in section 10 now. So let's just go ahead and start taking a look right over there, going onward. So jumping over, checking out section number 9. We got some material due today with the experiment and well, the tests and the uploads for the experiment. We'll go over a little bit of the aspects, we'll review of that, but ultimately we're transitioning into section number 10, which is going to focus primarily on vowel sounds. So we'll start looking at the human voice vowel sounds and noting that the vowel sounds are really nice harmonic sounds themselves. And we'll be doing some analysis, and ultimately you'll be analyzing your own voice, which is pretty cool to be able to do, see your signature voice and all the nuances within it. So this is where we are. Fantastic. And I'll just note a couple things here with this particular section, section 10, that the material for section 10, including the lecture and the quiz, isn't due for 2 weeks. This one can be a little time consuming, especially with having to record your own vowel sounds. And there's quite a bit to do with it, but there is no experiment test with it. It's just the uploads themselves. But within the uploads, some of the explanations are a little bit more lengthy, and there's some tables to produce and stuff like that. But that's something that we'll be going over. Just wanted to point that out that this particular um, material is not due for 2 weeks. Next week we will do some more things. We'll look at some percussive sounds and no real more experiments. This is kind of the last official experiment for the semester, other than your final project. So once we get through this, you should have more than enough information in terms of having the ability to start tackling something on your own in terms of looking at some sound or sounds and doing some analysis thereof. So let's just go ahead and start with the PowerPoint here. Dun, 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 dun. Make sure that I'm sharing the right thing. Yes. So welcome back, as I said. And at this point, finishing up section number 9, everything else in the books. And today we will focus on the topics being the voice and vowel sounds. We'll also have some reading to be attentive to, where we're looking at Johnson page 109 through 130, which has to do with the violin, and then 319 through 340, which has to do with the human voice. And ultimately, what we want to start being able to do is create, record, and analyze our own vowel sounds and see some general aspects of them. So, what we're going to go over this week is last week's experiment, and then the voice, human vowel sounds, vowel formation, and then the assignment, including the final project. We'll talk about that a bit. So first off, starting back with section number 9, we are ultimately looking at standing waves and the production of particular harmonics, production of pitch, and production of higher order harmonics as well. And we were looking primarily at I want to say open or open closed systems. We're looking at an empty bottle, a quarter wave pipe, a half wave pipe, and then your voice. We were looking at one particular vowel sound, but these are all standing waves that are inside resonant cavities. And what we wanted to do again was sort of look at these 4 different things, and especially with the quarter wave and half wave pipe, them producing very, don't want to say very, but fairly clear patterns of harmonics. We were able to, or hopefully able to, determine what the lengths of those tubes are based upon some formal aspects of physics. And again, basic points of the experiment: standing waves are correlated with the individual harmonics, and the length of the resonant air column determines the pitch for the quarter wave and half wave pipes. That is, the shorter shorter the air column is, the higher the pitch, the longer the air column is, the lower the pitch. And there was a direct relation with respect to that we had looked at in the previous lecture material itself. And boom, 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 we wanted to analyze the sounds, measure the frequencies, calculate wavelengths, and relate the length of the resonant air cavity to the pitch of the sound itself and see ultimately what the length of the air column had to have been. So some basic points once again for the air columns, for the open and open closed air columns. We have open tube. We have antinodes at each end, where the antinodes themselves are locations where the air molecules are undergoing maximal displacements as you vibrate back and forth. Whereas the open closed system has an antinode at one end, which would be the open end, and then a node at the other end, which would be the closed end. A node is a location where there is no displacement of the air molecules. And well, that has to be at a closed end because air molecules can't vibrate back and forth if there's a cap on the end, right? At that particular location. So those are kind of the boundary conditions for the systems themselves. And excuse me. And ultimately, we had some mathematical representation of what frequencies are going to be produced in terms of harmonic numbers and with respect to an open tube, sometimes called a half wave tube, or an open closed tube, sometimes called a quarter wave tube, quarter wave pipe. But for the open system, it was found that the frequency of the nth harmonic was that number n multiplied by v, which is the speed of sound in air, 1,128 feet per second, divided by 2 times the length of that air column itself. Inverting this around, really solving this for L, we get this expression right here, where, oh, you can come in. This expression where we have that the length L of the air column is equal to the harmonic number, which generally we'll just say is 1 for the first harmonic, V, again, which is the speed of sound in air, then 2 times the frequency. And in this case, again, if we're saying that we're looking at the first harmonic, that would be the fundamental frequency, F sub 1. And that's ultimately what you had to do, is figure out what the fundamental frequency is, and then from there, calculate what the length of the tube is based upon that for the half wave tube. And then you should also notice that when you look at the half wave tube, that there are other harmonics in there, but it's, while there's not a whole bunch, you should definitely see that there's a first harmonic, a second harmonic, third harmonic, fourth harmonic in terms of the multiplicity factor regarding the fundamental frequency. So you'll have another frequency that's 2 times the fundamental, 3 times the fundamental, 4 times the fundamental, and so on. They're not perfect systems, but they're pretty close for being just little tubes, basically cardboard. I think one of them's actually bamboo. But anyways, yeah, utilizing those to figure out some lengths, making some correlations with things. For the open closed tube, we got a very similar expression where the frequency of the nth harmonic is n times the velocity or wave speed divided by 4 times the length. But in this particular case, we only have odd integer multiples of the fundamental frequency. That is to say, there are no even harmonics. N can only take on odd integers. So we'll do have a fundamental frequency, F sub 1. There's no second harmonic, but there is a third harmonic, a fifth, the seventh, and such things. And again, solving this expression out for L, boom, oops, clicking the wrong button here. For L, we get that the length of the tube has to be equal to the nth harmonic or the harmonic number times the speed of sound in air divided by 4 times the fundamental frequency. And I am going to relocate really quick because I think I'm in a bad room. Sorry, you guys coming in here. Yeah, no, it's my fault. So, just give me one moment, please, while I jump over into another room. This one's going to be utilized here pretty soon. Apologies. How you doing today? Pretty good. Very nice. Good to see you. All right. Let me come over here. Listen really quick. We are set to go again. All right. Apologies, but here we go. So for the open close system, again, for calculating out what the length of the tube is, it's easiest to just use the fundamental frequency, F sub 1, and use n is equal to 1, calculate this out, v divided by 4 times the fundamental frequency, and you get the length of the column itself. One thing that I'll caution you in sticking this in, say, like a calculator, is that it's this quantity up at the top divided by this total quantity here, 4 times the fundamental frequency. So sometimes in calculators, you start sticking stuff in, and if you put in, say, 1,128, then divided by 4 times whatever the fundamental frequency was, your calculator will actually divide it by 4 and then multiply it by the fundamental frequency. So if you start getting these huge lengths, it's likely because you need to bracket this 4 times f sub n so that it's dividing the speed of sound by that whole quantity there. Another way you could do it is calculate out what 4 times the fundamental frequency is, and then do v divided by that overall quantity, and that'll come out good. So that's just something that could happen depending on what sort of calculator you may be using to calculate those numbers out. But again, odd integers only in terms of the harmonics, and that is something that should have been readily seen in the spectrogram slice, and that those big major peaks, there was one at the fundamental frequency, and the next one wasn't until you went over to a frequency that was 3 times the fundamental frequency. There was no harmonic at 2 times the fundamental frequency. So again, you end up with a first harmonic, third harmonic, fifth harmonic, and then after that, there's not much else you can really see. Degradation of the sound. But that's ultimately what we had going on. I'll say some more things. Fundamental frequency, always check it, double check, measure it in the waveform, figure it out with the period, look for it in the spectrogram slice, and make sure that you're actually getting it right. So you should have that your multiple ways of determining the fundamental frequency all agree with one another. If they don't, then something's going on wrong, and possibly you are picking the wrong one. So always confirm. Looking for the harmonics, seeing that they're integer multiples of the fundamental frequency. If you have blips in there, little peaks that aren't integer multiples of the fundamental frequency, those are not harmonics. They are just overtones, or they could possibly be something that's not directly connected with the sound that you're analyzing. It could be some background sound. But always want to be making sure that when you're looking at or looking for harmonics, that they are actually integer multiples of the fundamental frequency. Within reason, calculated out. You may get, hey, something's off by 5-7 hertz, something like that, percentage wise, relative to decently high frequencies isn't that big of a deal. But you always get a little variation in terms of nothing's going to be perfect all the time, just because of how we're measuring things and limitations with the program and just with precision in general. Again, in the waveforms, always look for periodic portions so that you know that you're looking at a harmonic portion. If you're looking in the waveform and it just seems chaotic, like, hey, there's no pattern here. Well, guess what? If you can't define a pattern, then you're not going to be able to find what a fundamental frequency is, because there isn't going to be one. There's going to be a bunch of overtones, and that's going to be it. So definitely make sure that you're looking in right spots. Telltale signs that you're not would be, again, a non-periodic pattern in the waveform, and or having non-harmonic overtones within the spectrogram slice if you were expecting there to actually just be harmonics. So here is a little bit, actually, I put the numbers in already, but just wanted to kind of go through this so that we could see something. Let me open up Raven here really quick. There's my Raven. So give this a sec to open up, but ultimately I want to go ahead and put in a particular sound, which is dun, 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 desktop. So, let's see. 1 second. 6-foot metal tube. That's it. So I had this metal tube. I was doing some little projects at home. I cut this tube down to 6 feet exactly, or exactly as possible with what I had, which was pretty close, and started making some open and open close sounds with it, basically tapping on the top of it and producing these little kind of plunger sounds. So metal closed. This is open closed. So open closed system. Let's go ahead, come over here, and you notice that you don't really see anything in here, but it may be a matter of amplitude, or maybe I'm just looking at the wrong file. So it really does not seem to be anything. That's interesting. All right, this definitely has to be the wrong file then. That is quite disappointing. Let me try this again. Dun, 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 dun. Just had the wrong one there. So 6-foot metal tube. This is open. And did I have these all set super high? There it is. All right. It's opening weird for me. And now it's not. All right. So let's take a little listen to this open 6-foot metal tube. Sound is being shared, which is not this now. Here we go. Ready? 1, 2, 3. So, metal tube. And then we could look at this waveform here. Let's look down here where stuff's already happening. Could zoom into that. Could zoom in a little vertically as well and see if we see a pattern in here. And while it's not the cleanest pattern, you can see you've got these two nice big sort of humps there. Then it comes down and does this little thing. And then it does the two big humps again, comes down, does this little thing, the two big humps again, comes down, does this little thing. It's attenuating. That is, it's dying off over time. It's getting quieter. It's a pretty quick decay that's going on, but yeah, that's where my hand's still hitting it. But we could focus on this part and say, what if we went from like, let's do this one. About there to about there, and said, hey, that looks like that should be one full cycle. Then from here to there would be another. And we go ahead and we look at the period here. So the period, according to this 0.10826 seconds. So I'll do 1 divided by that. 1 divided by 0.010826. And I get 92.37 all right, 90, 92 hertz or so. And we can come down and look in the waveform as well. So I'll just go ahead and spectrogram slice this over here. But notice that I'm going from, or not from, I'm going all the way out to 20,000 hertz. That's way too much. Let's zoom into just this first couple thousand hertz and see what we see in there. So zoom into that, kind of lift this up, and then we can increase the zoom levels vertically to sort of separate stuff out and see what we've got going on in here. And I'm gonna go ahead and uncheck that and then scroll this down. That's a little high. But there, we've got some, well, hopefully harmonics, but we've got some definitive overtones. Then we can start looking at them. Well, we can look at this first one and look at that. It says around 97. Yeah, so 97, 92. They not exactly agree, but they're within a couple of hertz of each other. And that was more likely that I measured it sort of a messily within the waveform itself. So let's just stick with 97. There's a second one about 2 times that. We come over to this, the second one, 97 and 97. Yeah, that looks about right. Maybe a little bit less, 184, 185. Yes, Lauren.
Yeah, maybe it's the way I'm looking at it, but is this tone periodic?
It is, but it's really, really quick because it's a very, very short sound. So the periodic aspect of it, let me come back into the waveform and zoom out a little bit. And what you'll see is really similar features. There is some little inconsistencies going on because this is just a big metal tube and it's not necessarily a complete circular cross section everywhere. It could have little dings in it. But if you see, we've got these two major peaks right here that repeat themselves in a very periodic way. And then we can look at what's happening in between them. And in between these two and the next two, you've got this little peak right here, followed by this little one. And you've got the same essence right here, except they're getting smaller. And things are really getting smaller and smaller overall because the sound, its intensity is getting lower and lower really, really quickly over time. So it's something that you still have this preserved pattern, but the intensity level of that pattern itself is getting less and less over really, really short amounts of time. So that produces some aspects, and things may not look exactly the same, but you still have the same overall sort of pattern here. So, for instance, I could look at going from, let's do these interior peaks. This peak's pretty nice. And I go to this second one and see what that is, 0.10718. So we get that for the time interval from that peak to the next instance of what I'm saying is the same peak. And then I can do it again and go from here to here and see if we get about the same amount of time. And it's close. It's not exactly the same, but 0.07, it's still right about the same. Here to here, 0.0, that should be like there, 0.007, 0.107. So you get that there's this preservation of this pattern, even though there's some things in between, some little nuances that may be undergoing some little fluctuations. And that's kind of, yeah, it is periodic, maybe not completely, but it's periodic enough where it's definitely composed of harmonics. So that would be something that we could see definitively within the individual frequencies when we look at the sound itself. So here, now I'm slicing it somewhere different. We have that this is a little bit lower pitched, and that's 93, then 189, 186 probably should be closer to And 3 times, that's about 3 times, 4 times, and so on and so on. If we look at the spacing between adjacent frequencies, we should be getting something back around 90 something, 92, 93. And that's exactly what we get. So even though there's some minor fluctuations going on, we still have something that is preserving the overall period of a larger pattern, I could just say. Yeah, these ones start getting out of whack a little bit. No, it's still around 92, 93. So is that okay? Does that still make sense? The pattern's there. Some little fluctuations going, and that's, I still consider it to be mostly harmonic, mostly periodic.
It makes sense. Thank you.
Got it. Perfect, perfect. So at any rate, we measure it out. We can see the instance of the individual harmonics here. You see that we do have some periodicity, and then we could go back and start making some calculations. So I picked 94 hertz when I did this, that particular portion of it. So let's just say we pick out the period, or we pick out that first harmonic. We say there was 94 hertz, right around there. From that, we could get the wavelength. The wavelength is going to be the speed of sound divided by the fundamental frequency. So you got 1,128 feet per second divided by 94 hertz gives us 12 feet per cycle. So that would be 12 feet in one full cycle of the wave itself. Now this is called a half wave tube because the wavelength is half the length of the tube. And that's ultimately why it's corresponding to, again, what we call a half wave tube. What happens if we take lambda and divide it by 2? Well, if it's 12 feet per cycle and we divide 12 by 2, we get 6 feet. And that is the length of the tube itself. It's a half of one full wavelength. Or we can go back with the expression that we had regarding the length corresponding to the harmonic number, the speed of sound, and the fundamental frequency itself specifically, and calculate this out with n is equal to 1 and f sub n being equal to 94 hertz. You stick that in and you get that the length is 6 feet. So either way, the aspect of the largest pattern fitting in there being 1/2 of a wavelength correlates with the length of the tube itself, or we can just calculate it out based upon the physics and the boundary conditions that we built this expression out of, which we didn't do in class. We just kind of offered it to you. But that's it. That's it. You can figure out the wavelength and you know whether it's a half wave or quarter wave tube. You can just take the wavelength, divide it by 2 or divide it by 4, or you can calculate out the length based upon whatever frequencies you're measuring in terms of the harmonic number and that particular frequency of it calculated out. Fantastic. So that's basically the idea, again, with the last experiment or section 9 experiment. Now we want to start going into some new material with respect to section number 10. So we want to start introducing vocal formants, and ultimately in acoustics and for speech science in general, a formant is just an area frequency wise and frequency space in a sense of broad maximums in intensity. So definition wise, usually defined as a broad peak or local maximum in the spectrum being the frequencies of which the sound is composed. Speech science and phonetics formant is the broad spectral maximum that results from acoustic resonance of the human vocal tract. In either case, formants are just locations, frequency-wise, broader locations where energy is being concentrated. So if you look at just the individual frequencies, you can say, oh yeah, this frequency has this intensity, this frequency has this intensity, and there's some overall individual distribution. But you can also look at things in terms of a more broad enveloping of where energy is concentrated across different frequency bands. And those are what we refer to as formants instead of just talking about individual frequencies. talk about broader areas where energy is concentrated. And that's going to determine certain aspects, certain uniqueness, certain characteristics of a given sound. So let's take a look at something right here. This is a spectrogram slice of particular sound. I don't recall what it is. I think it was me saying one of the vowel sounds, but I don't quite recall at this point. I don't have it marked. But anyways, here's a spectrogram slice. We've got a bunch of little frequencies here, right? They all look evenly spaced. There's a whole bunch of different frequencies. But look at this pattern overall that it makes. There's kind of this broader enveloping pattern that we had a lot of area, a lot of energy concentrated right around in here. And then there's this huge deficit of energy. There is not much energy here. The intensity levels of all the harmonics down in this region from about 800 to 1,800 hertz, there isn't much contribution. And all of a sudden, boom, some more contribution pops up from around 1,800 to 2,200. And then that kind of levels off. But then there's this larger area where there's a more or there is more energy being concentrated frequency wise. And then it again dies off. And then there's a little bit more over here. But what we want to look at is more of this enveloping. So this envelope of the spectrum is this right here. And I'll show you how to produce this within Raven. But this gives us not a clear picture of the individual frequencies, but more of the overall picture of at what frequencies is energy most concentrated and where is it not? Where is it not concentrated? So you can see we call this the first format. First format is going from 0 hertz to about 600 hertz or so. And then there's hardly anything. And then we get this increase. We got this more broad peak here, which we could call the second format. And then we've got this larger, broader peak, which we could call the third format. And some of that becomes subjective. Some may say we could call this whole thing the second format right here, because it's an area of general concentration. But the point is just to be able to point to areas within the spectrum for which there is more energy being concentrated than locally other locations, but not too specific, right? More broad. And that's what this graph is ultimately showing and what formats are really sort of about. So what we want to do is start taking a look at the experiment and how we're going to navigate through said experiment utilizing Raven. So we can open up the experiment on section 10. And first off, first thing that you're going to do is you are going to record your vowel sounds, your own vowel sounds. Hopefully you do not have issues with that, because it's so super cool just to be able to look at your own voice, to look at the nuances within the waveform and in the spectrogram slice, to measure your own individual fundamental frequency. And just it's kind of really amazing to start looking at your own voice and the human voice in general. But let this open up here. And if not, we'll let that open. And I will do this right now, in that while that struggles to open, I will first discuss how do you record and get that into Raven in the first place. So in order to record and open it with Raven, I would say the easiest way is utilizing Audacity. Because Audacity has a nice recorder in it. You've got a computer, you've used Audacity. It's pretty straightforward to produce a sound file and then export it and then open it back up with another program. Or if you've got a smartphone, they have voice recorders. You can record your voice with your phone, and then you can email the voice file or the sound file to yourself and then save it onto your computer. But with Audacity, it's already on your computer because that's where you're making it. So in Audacity, what I would want to do is first add a track, and you just want to do a mono track. You don't need any dual tracks here, stereo tracks. So I can add a track here, and then instead of generating a sound, just want to go ahead and record in here. So when we talk about vowel sounds, we're not talking about the letters A, E, I, O, U. We're talking about the sounds in terms of phonetics. Ah, E, A, O, U. And when you say these vowel sounds, what you should do for this particular experiment is say them all monotone. They should all have the same frequencies. And that's ultimately under your control. You don't want to go E, A, O, U. Then you're going to have different frequencies or different fundamental frequencies and harmonics for each one. What I'd like you to be able to do is produce these 5 vowel sounds all with approximately the same pitch. And that's again, could be difficult. Doesn't have to be perfect, but you definitely want to enunciate clearly and have each one be around a second or two long so that there's enough there where you can zoom in, you can see things and such. So I'm going to go ahead and record my vowel sounds and we'll go with this. E, A, O, U. Go ahead and stop it. From here, I don't want this other part here. It doesn't really matter, but I can just highlight this section here. My E, A, O, U. I could play it back. E, A. Let's not listen to that too much. But then ultimately, what I want to be able to do is go to File and go to Export, and I export this as a WAV file. MP3 is okay, but WAV files are better. They have more information stored in them, and we'll just do it. Let's save this as a WAV file now, and it says, where do you want to save it? Well, I want to save it somewhere I can find it. So I'm going to save it to my desktop just because that's going to be a nice way of finding this. And I can name it vowels 411, so I can find it. It's in WAV. If you do this with an Apple computer, it may ask you for AIFF. That's fine. WAV or AIFF, completely fine, both compatible with Raven, but I don't think you have the option here because I am not on a Mac. There is no AIFF. But yeah, if you can just stick with WAV, stick with WAV. I save it. Then it asks all this stuff. I don't care about any of this because I'm not an artist and I'm not publishing this. So I just say okay, and then it should throw a copy of this onto my desktop. So let me close this out. Don't need to save it. You can save yours so you have access to it, but we've got the sound file right there. There it is on my desktop. And now what I can do is I can take myself written and I can open the sound file, go to my desktop here, and there it is right there. Boom, select it, open it, physics of music, Cobam. And is that indeed my sound file? Oh, but sent the whole thing, that's okay. I can play this. E, A. Yes, indeed, that is my sound file. So what can we do with this then? Well, let's go ahead and look at the instructions and see what we're supposed to be doing. So kind of goes through once again, recording of vowel sounds, try to sustain them, make sure you're trying to do monotone. And what we want to be able to do is look at the spectrogram slices of each of these and ultimately the first 5,000 hertz or so. So we can do, let's just take a screenshot, use uncheck the waveform, take a screenshot showing all 5. So you should have something like this ultimately displayed. So if I go over to Raven and I say, oh, I want to have the vowel sounds and their spectrograms, I can uncheck the spectrogram slice, I can zoom in to those portions there. And then the first 5,000 hertz. Oops. We go back to the spectrogram slice. We're right about the first 5,000, but I can highlight 5,000 hertz in there, so it stretches that out from like 1 to 5. And then there you go, looking at about the first 5,000 hertz of each of these different sounds. And what do you see with these? A bunch of different striations, right? A bunch of different patterns. Each one of these is like a fingerprint. It actually looks very much like a fingerprint, at least a little bit. And well, these are sorts of fingerprints of these individual sounds that I have made as an individual. Each one of these dark lines is one of the frequencies in the sound. And you'll notice that, hey, look right in here. There's this area that's more white than dark. That's an area where there's not much energy concentrated. There's a big gap right in there. In this one, there's a whole bunch of gaps. Most of the energy is concentrated down here. So depending on what sound you're looking at, you'll have different areas of energy concentration. But all of the harmonics in all of these sounds are the same frequencies. Because I said this monotone, I will have the fundamental frequency within reason is the same for each one. If the fundamental frequency is the same, and these are harmonic tones, then all of the higher order frequencies are all going to be the same integer multiples of that fundamental frequency. So what makes these sounds sound different? It's not the frequencies, it's the intensity levels of the individual frequencies. Ultimately, it's where is energy concentrated? Is it concentrated in the low end and the high end? Is it sort of in a low and mid end plus the high end, or just the low, mid, and some other little locations? It really just depends. And that's what we be able to start appreciating and understanding, that the uniqueness comes from the timbre, which is all coming back down to the distribution of the intensity levels of the individual harmonics themselves. Where's energy concentrated? So again, this would be like one of the screenshots taken, so you can see your individual 5 sounds, and you can see the first 5,000 hertz or so of each of those sounds in the spectrogram. And then, well, let's come back to this and keep on going down. So now we want to go ahead and start looking at the selection spectrum view. We want to be able to make the envelope of the spectrum so that we can see the discrete areas where energy is concentrated. And I shouldn't say discrete, the broad areas where energy is concentrated, instead of just looking at all the individual harmonics. So eventually, what we want to be able to do is slice each one of these one at a time, look at the spectrogram slice, and also produce a selection spectrum, which gives us an enveloped view of the spectrogram slice. So what we do with this, we can come over here, take Raven, and I just want to go ahead and slice this here. Boom. For this, I'm going to remove the spectrogram, just look at the slice view. And first, just to note some things, you get the fundamental frequency, 123 hertz. Well, that's something that you probably want to double check with. I could zoom into that particular point in time and look at this. This is the waveform of my voice saying the ah sound. Ah, this is what the waveform looks like. Is that periodic? And the answer should be yeah, for the most part, that looks pretty darn periodic. There's again some little fluctuations occurring. Notice how small these little ones are compared to over here. Those are very minor little fluctuations. The periodicity of this is definitely something that is preserved. I see a repeating pattern over and over and over, not undergoing continual distortions, undergoing small distortions within a sustained pattern. And at that, you can see that all of these individual peaks here in the spectrogram slice are looking to be all evenly spaced, at least over the first, let's say, 3,000, 2,500 hertz. And then over here, you start getting that the contribution in terms of frequencies is very, very low. And this is more like noise in a sense. But over in here, we get a lot of good contribution here. So what we want to do is, again, introduce the spectrum selection and move these down. And dun, dun, dun. We've changed where things are. So selection spectrum, the tool to produce it is right here. So this is, it's not saying what it is. There it is. Selection spectrum view. So if I click on that, it's going to bring this up. Don't change any of this. This is already pre-configured. Just say okay. And it brings up another screen, but it says, oh no, the active selection is too short to compute a spectrum. And well, that's because the selection spectrum takes sort of an average value over some amount of time of the waveform itself. So what we need to do with this is, if I go back up into the waveform, I can zoom back out of it. Just zoom back out and then zoom back in. You notice that when I highlighted everything, it gave me something in the selection spectrum. Well, I don't want to highlight everything because now this is taking an average of all the individual sounds I said. I just want to look at this particular sound, which is my ah sound. So I can highlight a portion of it. Doesn't have to be a big portion, but whether it's big or small, it should be around the same if the sound was sustained nicely. But just get a portion of it, and here's the spectrogram selection here. Well, it does sort of follow the pattern of the spectrogram, as it should, but it's really hard to see like where definitive energy is concentrated. It's kind of flat, right? Well, that flatness is really a matter of zoom levels. There's not a whole bunch of room to be zooming in. So at this point, we could sort of get rid of the spectrogram slice view itself and just look at the selection spectrum. If we wanted to, we could increase the zoom levels. Oops. In the spectrogram selection spectrum to sort of get greater separation. And you can start to see areas of energy concentration right in there. Lack of energy right here. Another area with relatively low energy concentration compared to here. The vast majority of the energy in this particular ah sound that I've produced is within, say, the first 1000 hertz of the sound. And then it goes down to really, really low amounts of energy. Then it peaks back up a little bit where you've got between, say, 2000 and 2500 hertz. There's a little format there. But for something like this, I'd say that you've got one format here and then another format around in there. And those would be format 1, format 2. And you could talk about the individual frequency bands in which those formats exist in. Knocking this out. We come back over to the next sound. So let me get rid of that view for right now and come back to the spectrogram slice. What I want to note is that when I move the slice into the next sound, that the fundamental frequency still stays the same. And actually, all of these frequencies are still going to be the same frequencies because, again, I said this monotone. So let's just kind of see. Whoop, I move it over here. It's a little bit shifted. I did this a little bit higher pitched, but for the most part, 123 hertz. This one's more like 125 or so. 127. I went up in my pitch a little bit, but for the most part, we're going to have the same harmonics in here. But what do we have? A completely different pattern, right? Here's the pattern of the intensities of the individual harmonics in the ah sound. Here's the E sound. Much different. The ah sound, we've got that, what is this? The first, second, third, fourth, fifth harmonic is the most intense, contributes most to the sound, followed by the sixth, followed by, well, then we'd have to zoom in more to see whether it's the fourth or the seventh. It looks like it's probably the fourth, then the seventh, then the first. But if we come over to the E sound, it's the second harmonic that contributes the most, followed by the first, followed by the third, followed by the fourth. And then it looks like this would probably be the fifth most intense, sixth, seventh, eighth, ninth, 10th. And those are some things that you're going to be asked about. What is the first most intense, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th harmonic within the first 5,000 hertz or so of the sound? If I go back beyond that, oops, get that through the wrong thing. If I start looking at higher frequencies, I get the intensities are really, really low. Most of the energy is concentrated in the first 4,000 or 5,000 hertz. But again, we could look at the selection spectrum, highlight a little portion of this, switch on the selection spectrum, boom, switch that off, and you can see you got different areas of energy concentration. Whole bunch of area in the first 500 hertz, and then some energy. We could say that maybe this is a little format, and then this is a more large, broad format, first, second, third. But that's it. Identifying locations that area is generally concentrated. Do it for the third, do it for the fourth, third, start looking, fourth, start looking, fifth, sound, and they all have different overall patterns. And that's what the amazing aspect of this ultimately is. I have to take this off. Just super cool to look at where energy is concentrated in all these different frequencies. Anyways, that's the idea with this experiment, is just really looking at where energy is concentrated. So we get something like this, you take a screenshot, great, and then you identify locations where you have energy concentration. And for this, some of it's a little, again, subjective. Do I just call this one individual area right here, or do I split it into two? User judgment. There's no, I don't want to say there's no right or wrong, but some of it depends on how much variation you're taking into account with respect to identifying a format. We're not going to get into being really picky with this, other than just being able to say, hey, most of the energy is concentrated here. There's some concentrated here and some concentrated here, a little bit here, but comparatively, these three general areas are where energy is concentrated. So identifying those and describing stuff, describing what you're seeing, describing what those areas are, the formats, and then what you're going to do is do this for each of the four remaining sounds. So yeah, identify 2 or 3 general areas of highest energy concentration, and then also determine the 3 most intense harmonics in order based on intensity. So for instance, third harmonic, second harmonic, first harmonic are the most intense, where the third would be the most intense, second most intense, first, third most intense. So those are things that should be noted within your description itself. So what do you end up with? You're going to end up with 1 screenshot for this right here, and then 5 more screenshots for the formats. And if you don't want to have the spectrogram slice because it reduces your field of view too much, you can uncheck the spectrogram slice. Don't need that for this. Sometimes it's nice to be able to see it on top of each other, but that's going to be a matter of how much you can zoom in to see the individual areas of energy concentration. But all said, you'll have six screenshots, and make sure that you have descriptions for each, useful sentences. Take your time with this. You got 2 weeks, but ultimately, yeah, it's going to be you looking at your own voice. If you have troubles recording your own vowel sounds, there is an alternative. Oops. But I would much prefer that you don't use it, but it's this right here. You can download this sound, high pitch. Oh, this is just one sound. Sorry. Do I have my vowels in here? No, voice. No, don't use this. Sorry, that was for the last experiment. If for some reason you cannot in any way record your own vowel sounds and get them into Raven, email me and I will send you mine. But then you have to listen to my voice and or look at my frequencies, my harmonics, when it's much, much cooler to look at your own. So do try to get your own in there. And if you just can't get it to work, then email me and I'll send you some. All right. Going back down. Not gonna worry about that. That's something else. So start also thinking about your final project. Yeah, that was kind of the last thing I wanted to do with this. Thinking about your final project. What are you going to do? So make sure that you go through the criteria and general outline for the final project itself, which is in section number 9. If you have not looked at that yet, do make sure that you take a look. If you're a music major, I would just say you've got something to go with. If you're a singer or if you play an instrument, those are really general nice things that you can do. Everybody else, you can do whatever you want. If you're a speech pathology major or communicative disorder major, something like that, it's nice to do something regarding speech sounds. It's not necessary, but I would say, hey, if you've chosen that field to focus your attention to, then it'd probably be most appealing to you to do something that involves speech sounds. People have done a lot of things of comparing different accents, different different ways different cultures say different words, diphthongs, monophthongs, comparison of different vowel sounds that different people make themselves, not a reproduction of experiment 10, but something that grows on that. That's more than just that. But all said, the focus shouldn't just be on pitch. It should definitely be on, yeah, the pitch, the fundamental frequency, the other harmonics, their intensity levels. We've done a whole bunch of stuff other than just look at the fundamental frequency of a sound and get the pitch of it. Though that can be definitely a part. It should be about what else is in the sound, the timbre of the sound. What is the distribution of the intensity levels? We've got intensity ratios. We've got all sorts of stuff that we've done that can be embedded within some sort of formal analysis of a sound itself or a comparative analysis of a couple different sounds or a couple sounds that are similar but not quite the same. So generally, I'll say comparative analyses are probably easier to go with just because they give you something naturally to discuss because you're comparing two things. It gives you something to go with. Whereas just taking some singular sound and looking at it, it can be difficult to focus your attention on what are you gonna focus your attention on? Why the sound is the way that it sounds, right? But you pick something too general, like here's the sound of somebody talking. Well, where are you going to focus on them talking? What portion of them talking are you focusing on? So you've got to be able to narrow things down. There shouldn't be too much going on all at once, and it should be something that you can make sense of. 1,000 words at least. More is not necessarily better, but definitely something substantial looking for. And you've got a good amount of time to start thinking about it and start working on it. 1,000 words goes pretty quick. Definitely should involve screenshots, the use of Raven, explanations of screenshots, stuff like that. And here is a general outline type of how it should be constructed. You have a title, you have an introduction. What are you doing? You have parameters, any special things that you've utilized, And then results where you've got tables, you've got information, you've got the analysis portion of what you were doing and what it all means. And then a little discussion conclusion. What did you learn from it? And then appendices. I'm not a real big stickler on appendices, but if you're getting something from somewhere else, hey, cite it, have a little bibliography, but that's it. What sort of format? This format, I'm not really concerned whether it's NLS or whatever. This isn't an English class, but you still have to be able to disseminate information in a coherent way. So scientifically, this is generally a nice way of introducing something, saying how you set it up, explain your results, discussing your results, and having some sort of conclusions. If you follow that and do something decently thorough that makes some good sense, you're on a good path. All right. Questions? Then I will bid you a great evening and a nice week, rest of the week and nice weekend and all that good stuff. And until next.
Thank you.
Thank you. Bye.
Thank you. Take care, guys.